Assalamu alaikum. It's our 17th lecture of Advanced Electromagnetic Field and Waves. And in this lecture, we are going to solve modes in rectangular waveguides. We already derive the equations for TM mode and for the TE mode, transverse magnetic and transverse electric mode. As we know that for the transverse magnetic mode, the magnetic Z component is equals to 0, whereas the electric field Z component is not equals to 0. Whereas for the case of transverse electric mode is concerned, your electric field Z component is now 0 while your magnetic field Z components remains not equals to 0. And those equations for their other components x and y for the case of electric field and for the case of magnetic field has been derived in my previous video. You can watch from there. And for the case of the TEmodes, similarly the equations of Ex, Ey, Hz and Hx can derived in previous video. So we can start to find the modes in rectangular waveguide from these weak equations. So let's start our topic, which is the modes in rectangular waveguide. So let's suppose we have a rectangular waveguide. This you can see. Here you can see this is our length, which is considered as A, and this is our width, which is let consider as B. And inside the medium is mu epsilon, and this direction is the x direction, and this direction is basically the y direction, and definitely our third direction definitely should be z axis. Okay, now let's first solve for TE mode. As you know that for transverse magnetic mode, your magnetic field Z component equals to 0. So we have to only use our electric field equation. As we know that we have two equations. First equation is this: del square E plus K square E equals to 0, plus del square H plus K square H equals to 0. Okay, so this is our second equation. But in TM mode we have to only use the electric field equation, not have to use this equation, because in TM mode your magnetic field component is 0. That's why we are only starting our TM mode with this equation: del square E plus K square E equals to 0. Now here, first of all, what we have to do, we have to start with our equation. You can see here this which is, you can see here this. So what we have to do, we have to put the value of E of Z. E of Z is basically x, y, z in 3 dimensions, and del square you already know is basically Laplacian, and your Laplacian is, you already know that, is equals to del square by partial square by partial x square plus partial square by partial y square plus partial square by partial z square. Okay, so just putting the value of this is del square as it is, just putting the value of E plus K square, again this is the value of E equals to 0. Now what you have to do, you have to insert the value of del square, which is partial square by partial y x square plus partial square by partial y square plus partial square by partial z square, and you have to multiply each element with this. So you will get this: y and z remains constant for x, so yz comes out, you will get partial square by partial x square plus z plus xz becomes out for the case of y, so partial square y by partial y square inside comes, and x and y remains outside for the case of this z axis, so inside is partial square z by partial z square plus k x y z is as it is, k square x y z, kz k this equals to 0. Understood? Okay, now what you have to do is only have to divide your whole expression by x, y and z. Okay, you have to divide your whole expression by x, y, and z. So once you divide it by x, y, z, you will only left with 1 by x partial square x by partial x square plus 1 by y partial square by partial y square plus 1 by z partial square z by partial z square. And when you divide this by x, y, z, so x, y, z cancels with x, y, z, you will only left with k square equals to 0. Okay, now you know that your x and y are basically the standing waves. That's why their solutions must be in sine and cos form, while your z component is basically the traveling wave, which is in this direction or either this direction, outside or inside this page, z direction, and this is your traveling wave, and your traveling wave must be in exponential. So the solution of this is this a1 sine k1x plus b1 b1 cos of x, and solution of this y term is this a2 sine of ky plus b2 cos of ky, and similarly the solution of this z component, because this z component is the standing wave and your solution is now exponential, so it becomes a3 e power iota kz plus b3 e power minus iota kz. Okay, this is how you can write the solutions of this equation. So let's proceed. As I told you, your z-axis is basically the traveling wave, and x and y-axis is basically your the standing wave. So as wave node comes back for the case of your traveling wave, so this component now becomes equals to 0. You will only left with this. Here is this component, this is 0, so you will only left with this this equation. Now what you have to do, you have to use your boundary condition. So your Ez component is basically equals to 0 at x equals to 0 and at a equals to at x equals to a. Now what you have to do, you just have to initialize your Ez value equals to 0, and you have to put x equals to 0. So sine 0 becomes 0, so a1 becomes multiplied by 0, and cos of 0 becomes 1, so you will only left with b1, and this term's other side divide by 0, it becomes 0, so b1 becomes equals to 0. As b1 is 0, so a1 understood is not equals to 0. Now you have to put your second condition, x equals to a, your Ez equals to 0 when your x equals to a. So this becomes 0, and here where there is x, you have to put x equals to a. So it becomes a1 sine of k of x becomes a, as b1 is 0, so 0 multiplied by this becomes whole 0, so a1 sine of kx equals to 0. As I told you, a1 not equals to 0 because b1 is 0. If both is 0, then your solution is trivial solutions, but if b1 is 0, your a1 is not equals to 0. So sine of k of a becomes equals to 0 when when 0 when their angle is equals to n pi. So we get angle is ka, so ka must be equals to n pi if this condition is satisfied. So we can easily find the value of k of x, which is n pi by a. Now we have to apply our second boundary condition from figure. As I told you, we have two boundaries. One is the starting point is 0, and the ending point is for length is a and for width is b. So our second boundary condition is our Ez equals to 0 at y equals to 0 or x equals to b. Okay, so what we have to do here is, again we have to put the value of y0 in this equation. So again this sine 0 becomes 0, so your a2 becomes 0, so a2 multiplied by 0 becomes 0. Now b2 cos of 0 becomes 1, so b2 now here is equals to 0. Now you have to put your second bounding condition, which is x equals to b. Now b2 is 0, so this becomes only 0. You will only left with this a2 sine of k, and y is b, so kb, and again sine is equals to 0 when it is equals to m pi. Because we have to introduce a new constant before we introduce n, now we are introducing just m. So kb must be equals to m pi, and because we need the value of ky as we find kx, so ky becomes equals to m pi by b. Understood? Now what we have to do, we have to insert all these values in our main equation. This is our main equation. In main equation, b1 is 0 and b2 is 0. So this and this becomes 0. You will only left with a1 sine of this, a2 sine of this, and a3 exponential of this. So a1, a2, a3 remains constant, comes outside, and sine of this, and exponential becomes this. Now a1, a2, a3 becomes a new constant, and that constant name is, let's suppose, as e naught. So e of z x y z becomes equals to e naught sine of, and by putting the value of k of x, which we find n pi by a, and so it becomes sine of n pi by ax, and by putting the value of k of y, which is m pi by b. So this is your expression for e of x. Understood? And the expression is in e of z equals to e naught sine of n pi by ax sine of m by b by y m pi y by b multiplies by exponential power iota k z. Understood? Now move further. Now for TM mode, we know that we have to find the components of e of x, e of y, h of x, and h of y. How we can find those components? So first of all, we know the expression of e of x in case of TM mode, which is this iota k divided by r square partial ez divided by partial x. Okay, what we have to do, as we already find e of z before, so by just taking the derivative with respect to x of ez, we can easily find the expression of e of x. So let's take the derivative of ez with respect to x. Iota k r naught, which is constant, remains outside, and e naught is a constant of ez, comes outside. By taking the derivative, because inside is here is sine and here is sine, because we have to take derivative with respect to x, so only x terms derivative changes. So derivative of sine is cos, so it becomes cos of n pi by a x, and y terms remains constant because y is constant for x, so it becomes outside, so that's why it not changes. And exponential is also not changes because this is z component. As you take the derivative of x term, so sine of n pi a x convert into cos of n pi by ax, and d by dx of their angle. So angle derivative is this n pi by a. So n pi by a constant multiplied by this constant, it becomes your e of x becomes equals to iota k n pi divided by r square a e naught cos of n pi by ax sine of m pi by b y multiplies by exponential iota kz. So this is your expression for TM mode of e of x. Now how we can find the expression of e of y? We can easily find, because we have a value of e of y, okay, in TM mode, and we know that the expression of e of y in TM mode is e y equals to iota k divided by r squared partial ez divided by partial y. You just have to take the derivative of e of z now with respect to y. Here you take with respect to x, now here you take with respect to y. The only difference is this. Again, the constants remains as it is outside, and now your x term not changes, now your y term changes. Your sine becomes equals to cos, and this, and angle's derivative is this m pi by b, and this is as it is. Okay, so constant multiplied by constant becomes iota k m pi e naught divided by r square b, and angle remains as it is. So this is your expression of e of y. Now we also need the expression of h of x and h of y in case of TM mode. How we can find those components? We can easily find. We also know the expressions of h of x and h of y in term of TM mode, which is this iota minus iota omega epsilon divided by r square partial ez by partial y. It means just taking the derivative of e of z, we have the equation of e of z. By just taking the derivative of e of z, we can easily find the expression of h of x, and this remains constant because these are constant remains outside, and the ez constant is e naught. Now you just have to take derivative with respect to y. Again your y term only changes, x term remains same and z term remains same. You have to take only y term derivative, and it becomes cos of m pi by b y, and the angle derivative of this multiplied by this, your final expression is this. Simple. Minus iota omega epsilon m pi e naught divided by b r square, and sine term, cos term, and exponential term with them. We also know hy component in Tm mode, which is this iota omega epsilon divided by r square multiplied by partial ex by partial x. Means you just have to take the derivative of Ez with respect to x now. Again this is constant remains outside. Now your x term changes of Ez. Now it becomes cos of n pi by ax. Now angle derivative is this n pi by a, and your y term and z term remains constant, and this is your final expression for h of y. So these are the final expressions of e of x, e of y, h of x, and h of y. Similarly, now move on towards our TE mode. Again we have to do the same procedure for the case of TE mode, transverse magnetic electric mode, and we have to find the similar cases of e of x, e of y, h of x, and h of y. Now move on towards the TE mode. This is TE mode, transverse electric mode, and in this your Ez is term is basically equals to 0, and your hz term is not equals to 0. So we have to start with the hz equation. So your hz is split into x and y and z component, as we splits for TM mode the E components. Now in TE mode we have to split the H components here. Now by separation of variable, our equation is this. Just put the value of H, which is xyz here, and k square as it is, and H values xyz is here. Now again open the Laplacian del square, which is partial square by partial x square plus partial square by partial y square plus partial square by partial z square, multiply by this whole. So when partial square by partial x square multiply by whole, y z this constant comes out and x multiply inside. Similarly for the case of y, y is inside, x z is outside. For the case of z, z is inside and x y is outside. And k x y z is this equals to 0. Understood? Okay. Now what you have to do is you just have to divide your whole expression by xyz as we did before. So after dividing your whole expression by xyz, you will get 1 by x partial square x by partial x square plus 1 by y partial square y by partial y square plus 1 by z partial square z by partial z square plus k square equals to 0. Again, as I told you, your x-axis and y-axis basically the standing wave. Their solutions must be in sine and cos, while your z component is basically the traveling wave, means into or out of the page. So that's why the solution must be in exponential form. So these are basically the solutions of x, y, and z components. Okay, this can be written as this. Okay, now before there is no wave that is coming back for the traveling wave, which is the z-axis. So that's why this term, reverse back term, now becomes equal to 0. So you will left with these equations, this and this part only, and this becomes equal to 0. Now again you have to put the boundary conditions, because we have not h of x boundary conditions. We have only electric fields boundary conditions. So what we have to do, we have to convert our hx into, we have to convert our hz into az by using our equations. So as we see our equation, so these are our two equations. We can see if our e of x equals to iota omega mu divided by r square partial sz by partial y, and ey equals to minus iota omega mu divided by r square partial hz divided by partial x. From where this equation comes, you can see these equations from our previous video, where we derived the 4 equations for TM mode and 4 equations for TE mode. These 2 equations are one of them. Okay, please watch from confirm from those videos. Okay, total we derived 8 equations, 4 for TM mode and 4 for TE mode. these two equations comes from those equations. You can see we can easily convert ex into hz, and we can easily convert ey into hz. Now these are the expressions of e of x and e of y. Okay, you just have to put the value of, just have to take the derivative with respect of h of z with respect to their respectives as shown in the equations. Okay, so this is now equation b, and this is now becomes equation c. Okay, now what you have to do, you have to put here your boundary conditions. Your boundary condition is basically your is similar. Your e of y becomes equals to 0 at x equals to 0 or x equals to a. Okay, now means this becomes equals to 0, and you have to put x equals to a, x equals to 0. So once you put x equals to 0, sign becomes 0, you will only cos 0 becomes 1, you will only left with a1. So a1 becomes equals to 0. And second boundary condition, a equals to x equals to a, you have to put, because a1 is 0, now you have to put your here, so it becomes b1 sine of k a, and again sine is 0 when your angle is equals to n pi. Again kxa equals to n pi, so means kx equals to n pi by a. Okay, now you have to put the second boundary condition, which is now e of x equals to 0 at y equals to 0 or y equals to b. Again you have to put the value of y equals to 0 in this main equation. So once you put y equals to 0, your sign terms all goes out, your b2 and cos 0 becomes 1, means b2 equals to 0. So here you can see, sorry, this becomes sorry, your ex, this is the expression for e of x. So in e of x you have to put y equals to 0. So once you put y equals to 0, your sign becomes 0. Okay, because sine 0 0 and cos of 0 becomes 1, so you will get a2, and a2 becomes equals to 0. So you can see a2 becomes equals to 0. Okay, and you have to put y equals to b in again equation ex equals to 0. So ex equals to 0 equals to, as your a2 is 0, so you will left with b2 minus b2. Okay, minus b2 and minus b2 and sine of b. Again sine of angle is equals to 0 when the angle is m pi. So you can easily find the value of k of y, which is m pi by b. Okay, now what you have to do, you have to put these values in your main equations of h of z. As you know, your main expression of h of z, which is before, and you just have to put the value of a1 equals to 0, a2 equals to 0. You will only left with b1, b2 and a3, and these are your remaining expressions, cos of m pi x by a and cos of n pi x. Okay, y by b exponential powers is same, and these three constant multiply becomes a new constant, and this becomes h naught. Understood? And now hz equation is here in front of you, which is e naught cos of m pi x by a and cos of m pi y by b, and multiplies by exponential, which is same. Now what we have to do, we have to find the expressions of e of x, e of y and h of x, h of y for the case of TE mode. Okay, so for the case of TE mode, first of all we need those equations of ex. First of all, let's find e of x. For that we need a equation of e of x in which there is h of z. So this is one of the equation, e of x equals to iota omega mu divided by r square, in which there is h of z. You just have to take derivative of h of z with respect to y to obtain the equation of e of x. So I just take the derivative of this equation of h of z with respect to y. Only y terms you can see changes. Your x term constants and z terms remains as it is. And taking the derivative of y term, it becomes sine of n pi by by multiplied by their angle derivative, which is n pi by b, and this is your final expression for e of x in TE mode. And how you can find for ty? Similarly, we need an equation of t of y in which there is h of z must become. So this is one of the equation from those 8 equations which we find earlier. Okay, so you just have to take the derivative of h of z with respect to x. Okay, so only x term changes, your y term, your z term, and your constant remains same. You just have to take the variables of h of z where there is x. So it becomes a sine of m pi by ax and m pi by a. So this is your final expression of e of y. Now we have to find the expression of h of x. We need a equation of h of x in which there is h of z, because we have a general equation of h of z right now. That's why we need a equation of h of x in which we have h of z. So this is the equation in h of x which have inside h of z. And you can see we just have to take the derivative of h of z with respect to x to obtain h of x. So only x term changes, your y and z remains same and constant remains same, and this is the final expression for h of x. Similarly, h of y equation you can find easily by taking the derivative of h of z with respect to y, because we have an equation of h of y in term of h of z, which is this equation. So by taking the derivative of h of z, we have general equation, and taking derivative with respect to y, we can easily obtain the expression for h of y. So only y term taking derivative transform into this, your x term, your constant, and your exponential terms remains as it is, and this is your final solution for h of y. So that's all for today's lecture for advanced electromagnetic field and waves, in which we find modes in rectangular waveguides. We can upload more interesting videos for this course, advanced electromagnetic field and waves. Till then, take care. Allah Hafiz.